So when we first look at LOL charts, they're not really L's, they're actually graphs. These are the initial conditions. This is going to be the system, and these are going to be the final conditions. And the system in this case is this cup of hot coffee. So this cup of hot coffee right here is going to be our system. And it says that it cools as it sits on the table. So I've got here my particles of what it looks like when it's hot. They've got longer things here. They're moving faster to when it cools down and it's moving a little bit more slowly. When I work with my LOL chart, the kinetic energy is going to be directly related to the temperature. So a higher kinetic energy is going to be related to a higher temperature. The reason that kinetic energy is related to temperature is because the faster the particles are moving, the more movement, the hotter the particles are. So kinetic means the energy of movement. We're looking at the movement of the particles. In our LOL charts, potential energy is actually going to be the energy of the state of matter. And this might be a little bit different than physics class, but what we're going to use as our standards is we're going to say if the substance is a solid, that's going to be equal to 1 block. If it's a liquid, we're going to go ahead and every single time we're going to use 2 blocks. And then if it's a gas, we can always use 4 blocks. So you might be asking, why does a gas have 2 more blocks than a liquid? Why didn't we go from 2 to 3? Why did we go from 2 to 4? Well, if you remember our heating curve, especially for water here, the ice heats up, it melts, the liquid heats up, it boils, and then the steam can heat up. It takes more energy for the liquid to boil than it does for the ice to melt. And that's because the particles are so much different in a gas. They're spread apart so much more. So we'd like to represent that for our PE, which is the energy of the state or potential energy. So in this case, we've got coffee. So coffee, we know, I like to start with the PE because it's really the easiest. We know that coffee is a liquid, and it says that it cools on the table. So it's going to stay a liquid, all right? We haven't changed the coffee at all. Now we need to make sure this whole time that we are working with exactly the system that we want to be working with. So we write it in there. So we know that this whole chart is about coffee. But what is happening in here is it is cooling. So to show cooling, I'm going to show that the kinetic energy goes from something hot to something cooler. And I just took away 1 block. These can be different if you wanted to go from 4 to 1 or whatever, but I like to keep it, kind of close to what you'd expect this to be at room temperature, if possible. So that's why I chose to go from 3 to 2. So what happened was as it cooled, this block right here was released. So I show it as just 1 block coming out of the system. And that block is that block. So then, as you can see, I'm left with these 2 blocks after. So let's do another one. This time we have a can of cold soda. So can of cold soda is my system. So I'm going to go ahead and write soda in here, which, pains me because I do want it to be pop. And it's going to warm as it's left on the counter. So initially, it's cold. That's why I'm choosing blue for my particles. There's not much movement in the particles. I'm trying to show that. Since we want our particles to be countable, I'm trying not to use too many so I don't have to draw too many particles. And after it sits there, it's going to warm up. So I'm going out of my way to make these particles appear to be moving faster. So let's work on the LOL chart. The soda stays a liquid again. So potential energy stays from a liquid to a liquid, only this time it's going to warm up. So maybe it started as like ice cold and then it ended at room temperature. So this time the arrow has to go in to show that a block was added. And this is the block right here that was added, and we added it right here to kinetic energy. All right, then they start to get a little trickier. This time we have a tray of water at 20 degrees is placed in a freezer and turns into ice cubes. And these ice cubes are going to be below freezing. So we're going to go all the way from liquid water at 20 degrees down into ice, and then we're going to cool the ice to -8. So part A says, how does energy transfer when the water is cooling down to 0 degrees? And I wrote here, hint, it's not ice yet. So the system is my tray of water. And you can write, if you want to write tray of, probably the most important word there is water. So again, we're just in the liquid phase at this point. It hasn't changed, but we're going to cool it down. So we're going to go from here, and we are really approaching ice cold. So I'm choosing to go from 2 blocks, which is, like room temperature, down to ice cold. And I'm going to show that by inserting a block. Notice I put it on the bottom. It doesn't really matter. Oh, I'm sorry, and I made a mistake right there. And as I was about to highlight it, I realized a block is leaving. And I realized it because I went to color it. So this block came out of the system. So just like the example above, really the particles are going to look very similar to this. Initially, it's going to be warmer, and then it's going to cool down to that. Now, the next problem says, okay, now we have cooled the water, but what happens when that water freezes from a liquid to a solid down to -8? Now, they've gone out of their way to tell you the states of matter and the temperatures. So we've got a little bit more happening. I'm going to start with the potential energy. Again, we have a liquid, but this time, finally, we're going to go to a solid. So we're going to go from 2 blocks to 1 block. I don't like the way I drew that there, so I'm going to kind of come through and make that block kind of match the other side. In addition to that, I am also watching these ice cubes get colder. They're going from 0 degrees to -8. Since we can't have half blocks or anything like that, I'm going to have to represent 0 degrees as 2 blocks and then -8 as 1 block. So there's nothing set in stone that says you have to use a certain amount of blocks for your kinetic energy. But in this case, I have, again, my tray of water. What I have here being released is actually 2 blocks. And one of the blocks is kinetic energy being released, and the other block is potential energy being released. And you can see we go from 4 blocks over here to 2 blocks over here. So we have overall kinetic and potential energy that is all being released as heat energy. Okay, it's all the same kind of energy. Now in this one, I love this one. So we have the question, where does the energy that leaves the system in number 3 go? So remember, number 3 was all about this tray of ice cubes that we had in the freezer, and that tray of ice cubes got cold and it froze. And we know that that tray, as we wrote there, released 2 blocks of energy. So it wants to know, where did these blocks go? Well, it left the water, It went into the freezer, and then ultimately, this energy that left this is going to go into the kitchen, because the rest of the problem says, how does this energy transfer affect the room temperature in the kitchen? Fill out the bar chart to help you answer this. So I'm going to go ahead and I'm going to write kitchen in here, right? And I can remember that 2 blocks came out there as heat energy. So I'm going to go ahead first and foremost, and I'm going to make 2 blocks enter into my kitchen. Now, the potential energy gets a little bit wonky here, because if you're talking about a table in the kitchen, you're talking about a solid. If you're talking about the air in the kitchen, you're talking about a gas. So quite honestly, your potential energy doesn't really matter there. But what does matter is that your kinetic energy is going to increase. And in this case, I did show it increasing by 2 because I wanted to show it, being the same from the last problem. But that doesn't necessarily have to be the case. So what happened here was that my kitchen got warmer. So believe it or not, when you put a freezer in your kitchen, it actually warms up your kitchen. It would feel like that would be the opposite. So again, these 2 blocks are these 2 blocks that came in as kinetic energy. Now we're getting even trickier. One of the ice cubes described in number 3 is placed in a glass of room temperature soft drink. Do separate bar graphs for the ice cube and the soft drink. All right, so this one is going to be my ice cube, and this one is going to be my drink. So let's start with what we do know. We know that the ice cubes are going to go in the soft drink. So we know that they start at least as ice. Do they melt? Now this is going to be up to you. I suspect that the ice is going to melt into a liquid. But if you just imagine the ice cooling down, that's okay. So 1 block is a solid, 2 blocks is a liquid. And that always stays the same. That is a rule that we are going to live by. Solids equal 1, liquids equal 2, and gas equals 4. So I'm imagining the ice cube is going to melt. As far as the drink, it's a liquid. It's going to stay a liquid. What's going to happen to the kinetic energy of the ice cube? Well, the ice cube is going to get warmer. I don't know why I drew it like that. That looks kind of funny. There we go. So I'm going to add a block in. So the ice cube has 1 block that enters it. And that block is right here, that kinetic energy. So that's showing that it entered as kinetic energy. It warmed up. But I also went out of my way to change it from ice to a liquid. So I actually need to add a second block. And that second block is representing the potential energy. So I'm adding 2 blocks of energy. So if I'm adding 2 blocks of energy, then I would guess that my drink also is going to lose 2 blocks of energy, right? Because the ice cube is getting its energy from the drink. So I'm going to show that in kinetic energy. I'm going to say that I had, kind of a warm glass of room temperature soda there or something, and it cooled down to icy cold. So right here, these 2 blocks were given away to leave those behind. So in this way, the LOL charts can trace energy through a system. It says, describe how the arrangement and motion of particles in each system change. Well, These particles are going to move faster, and they're going to turn from a solid, nice and orderly, to a liquid, a little bit further apart. These particles are going to be a liquid, and they're going to slow down. So they have opposite effects on the ice cube and the drink. So I hope that gives you a good idea of how to work an LOL chart in chemistry.